Welcome back to COS 217 lecture. This is the second half of our machine language coverage. Thus far, we've seen what instructions look like in machine language, but that wasn't the whole story. The instructions we've seen only had references to other locations that were known at assembly time. For example, a jump to a label that's 4 instructions later in the code. That won't always happen. For instance, what happens if we call a library function like printf? We know from earlier in the course that this is where the linker comes in, but now we'll get to see how the assembler lets the linker know what it needs help with, and then what the linker actually does. To dive into this, we need a program to study. Here's a program that prompts the user to enter a character, checks if that character that was entered is the capital A, and prints hi if it is. The program isn't very interesting on its face, but let's look at the assembly version, which references labels within our own text section, within another section, and in the text section but contained in another file that we don't have access to at assembly time. In the RODATA section, we have the prompt string followed by the hi message string. Then we go into the text section, and after our prologue, we have an ADR of one of those strings and then a call to printf, which is of course found in an external library. We also have a call to getchar, again found in an external library. Then there's a conditional branch that jumps to another spot in our own text section within this file. There's another ADR referencing our RODATA section, and another call to printf. After the skip label, there's the conventional setting of the return value, the epilogue, and the ret instruction. So now we have to answer, what does the assembler do to generate machine language for this when it doesn't know what addresses or offsets are for several of these references? We can see exactly what the assembler generates in a .o file by using the objdump command, which will potentially prove useful in assignment 6. Perhaps surprisingly, we don't actually see any addresses here. We see that RODATA starts at 0. Surely that's not a valid address. And in fact, using only what we've learned in this class, we can prove this can't be the address. String literals are what we store in RODATA, and we can dereference them, for example, to print them or to see what the first character is. Only for reading, of course. But we can't dereference null pointers, and null pointers are pointers that point at the address 0. Thus, this better not be an address. And indeed, it also makes sense for another reason. We've learned that finalizing the address of each section in the executable is the linker's job. But now, if you think about it, we can reason that the assembler can't do it. Think about if you have a module like your string module, or symtable, or bigintAdd. There's no way the assembler can possibly know, when creating stra.o or symtablehash.o or other implementation object files, what clients will end up linking against them. So it can't finalize any of the addresses for things in your module, because that would risk a conflict if the assembler for the client of the module put something else at that same location. So at this point, we can't have addresses, but we can have offsets, displacements from other things. In this case, the start of this file's entries in RODATA. This file's entries in RODATA will eventually be combined with other files' RODATA sections, but they will be held together, they're contiguous. The assembler has enough information to know right now the type char is the first string in the RODATA section that it knows about, so let's call that offset 0 for now. Hi is the second string, it comes right after it, and since the prompt string has 14 characters, remembering the null byte, hi can start at offset 14, which is hex E. With a different set of command line arguments, objdump can also show you the text section, and even do the disassembly for you so that you can read your previously dreaded but now hopefully super comfy assembly language rather than having to read the machine language directly. This is perhaps more useful if we have an arbitrary .o file instead of just a .o file built from code that we already had. Note though that the machine language is there. The 8 hex digits are a compact way of representing the 32 bits in the instruction, so you can, if you want or need, expand these out to get the full 32-bit string for the instructions like we saw last lecture. We'll dive into the actual instructions in a second, But first, let's just look around at that first column of the output from objdump. Just like with the RODATA section, the assembler can't generate actual addresses for the instructions. The reasoning is the same. If the .o files had addresses, then there would surely be conflicts that would arise. For example, the assembler put some local function in detect_a .o in the same location that the assembler way back when put printf in stdio.o. So these are just offsets. We're counting by 4 because each instruction is 4 bytes. When we have a label like main or skip, it appears to have an address, but again, it's just the offset. So again, let's look at each of these instructions one at a time now. At offset 0, which is to say the beginning of the text section in this source file, we have the beginning of main's prologue, a subcommand to make space for main stack frame. When we expand out the hex machine code, D to 1101, 1 to 0001, and so on, we see each individual bit. But of course you aren't expected to remember all of the components of the instruction, so perhaps at best I can hope that you'll remember the last 5 bits are the destination register, and actually yeah, that looks right. 5 ones makes a 31, so that's SP. It would be handy if I could pull up the formatted slides from last time, so let's do that. Here's what a sub looks like, primarily as a reminder. The operation group bits within the full opcode are in burgundy. The instruction width, whether to use 64 bits or 32 bits, is in pink. The determiner for whether or not this instruction sets the condition flags in P state is in cyan. The second source operand, in this case an immediate, is in orange. The first source operand, the register SP, is in green. And as noted before, the destination, also register SP, is in blue. So far so good, exactly like we saw in our previous lecture. The next instruction was the second part of the prologue, stashing the value of x30 onto the stack so that we can recover it to be used by the ret instruction at the end. Again, nothing new here. We're storing an 8-byte value, so the width is 1, 1. We're storing it into location that SP points to, not an offset, so the orange offset is 0. This is a store, so the usual semantics of source and destination are flipped, and thus we're storing x30 in blue into the location that register SP points to in green. The third instruction is the ADR to get the prompt's address into x30 in order to pass that, into x0 in order to pass that to printf. But this is weird. It says main there, not message 1. Recall that ADR was a bit funky, with the disconnected relative address, with the more significant bits of the relative address in orange and the disconnected least significant bits in green. But okay, let's parse it out. The opcode is normal. The destination register is 0, which corresponds to x0, so that's good. But when we put together the two parts of the relative address, we get 0. But if it's 0 bytes away from this instruction, doesn't that make it this instruction? But this instruction certainly isn't the prompt string. This is in fact a placeholder left by the assembler, because it can't finish the job right here. Message 1 is in RODATA, this instruction is in text. The assembler has no idea where those two sections will go in the final executable, so it can't know the distance between this instruction and that label. So it leaves zeros as placeholders, and it will need to leave a message for the linker to say, this is just a placeholder. When you figure out the location of RODATA and of text, can you do the subtraction and fill it in here? Thanks. Going back to the output from objdump, perhaps you've noticed that we've been ignoring a bunch of lines, going so far as to gray them out on each of the slides. Let's look at them now. There are, after some instructions, annotations that list the offset of the instruction and some other information. These are relocation records, which are annotations that the assembler will leave for the linker. Plaintive calls for help, if you will. Here's our first one. It's a bit cryptic. We see the 8 is the offset of the ADR instruction that the assembler couldn't finish. We see some big string that has AART64. Okay, that's the name of the ARM architecture. That makes sense. And an ADR, which we might guess either represents the word address or it corresponds to the instruction that needs fixing. As it ends up, it will be the former. And then there's some other substring that doesn't really mean much to us. And then we see RODATA, the section that the assembler didn't have enough information about, but there's just too much here. It's hard to pull together. Here's how we can decipher it. Here's how we can look at a relocation record. Again, it's a plaintive plea from the assembler to the linker. So let's imagine it as a sort of formal requisition order. 8 is the offset in the text section that contains the instruction that needs to be fixed once the linker figures out where it puts stuff. RODATA is in fact the architecture. It's asking for an address relative to this instruction, that is, relative to the PC. So prel is program counter relative, and that's the program counter when that instruction is going to be executed. It notes that there's room for 21 bits, and that these will be the low order bits of the relative address of this instruction. It notes that the RODATA section address is the address that's needed, in addition to the address of the text section to fill in what is here, after all. We could note really this is RODATA plus 0, because we're not looking for the address of the RODATA section itself, per se, but rather the address of message 1, which is at the 0 byte offset from that section. So this is all of the information the linker is going to need to fix up this instruction into its final form for the executable. That's one relocation record down, 4 more to go. Our next instruction is the BL call to printf. Now that we know a little bit more about placeholder data in instructions, we can see just from the hex that this is going to have a placeholder in it. We're certainly not branching to memory location 0, so let's take a look and see what this placeholder is doing. Indeed, we have an opcode for BL, then the entirety of the relative address is 0. The assembler needs to calculate the relative address between this instruction and printf, but it doesn't know where printf will be. It's off in another file. Printf's label, needed to complete the relative address, won't be here until the linker does its thing and gathers up all of the functions that are referenced to shove them all together into a unified text section. So the assembler is forced to fill in a placeholder of 0. And now, the assembler will tell the linker what it has done and how the linker can fix it with another relocation record. So here is that relocation record. Let's dive into it again, continuing our play on the form of a prim and proper written correspondence for consistency, and also because I'm really hoping that the ridiculousness of the tools running the build process having this stodgy, aristocratic, Julian Fellows-worthy messaging is enough to make it stick in your mind. So let's go step by step. C is the offset in the text section in this object file that contains the instruction that needs to be fixed once the text sections are finalized. RODATA is again the architecture. The assembler is asking the linker to fix the relative address in a function call, which consists of 26 bits. The function it needs is the address for is printf, and it needs it in order to subtract that address from this instruction's address to generate that relative address. So again, this is all the information that the linker needs in order to fix up the instruction into its final form for the assembler, completing the assembler's work and putting it into the final executable. So that's 2 relocation records down. 2 more to go, but they'll be of the same form that we've already seen, so the hard part is behind us. This is a good point to stop and go back and look at these first 2 examples to make sure you've got it before we move on. We turn around from calling printf and we immediately call getchar. Again, that 0 is the target of the BL, portends that the assembler can't finish the job here either, and it makes sense because getchar again is in the standard IO library. So again, with a BL, we have a 26-bit relative address that the assembler fills in with all zeros, just like for printf. And again, the assembler will leave the requisition order for the linker, asking that it patch the proper 26-bit address of relative between getchar and the current instruction. And it will do that at offset hex 10, wherever those 2 addresses end up being. After the call to get char, we have to figure out if we read A or not. We'll do a comparison between W0 returned by getChar and an immediate value. Hex 41 is the ASCII code for capital A, decimal 65. Perhaps you recall from a few lectures ago that CMP is really just a convenient, semantically meaningful alias for subtraction that sets the condition flags and throws away the results. So when we look at CMP, the opcode is actually that for subs, subtract with setting the flags. In this case, it's subtracting an immediate. It's a W register, so the width is 0 because it's 32 bits. The cyan bit 29 is a 1 for yes. The whole point of CMP is to set the flags in P state. The sources are the register 0 and the immediate value hex 41, decimal 65. And because setting the bits is actually all we want to do, we're happy to throw away the result. And so the destination register is WZR. That's the always 0 register, which we can write to with impunity. It won't change anything no matter how often we write to it. Note that this instruction then uses 31 for WZR, as opposed to some of the others we've seen that use 31 for SP. And as a reminder, if you ever need to check for any given instruction whether the register encoding 31 is SP or WZR or XZR, you can go and check out the very first ARM precept handout, which lists that. The next instruction is another branch, but it's different because this time it's not calling BL on some external function. Instead, it's a conditional jump to just another spot within the text section that's defined here in this file. In terms of the C code, it's saying, if we didn't read A, don't print high. For this instruction, the assembler has what it needs to complete the instruction. It will be exactly as we saw it in the last lecture. We know the offset of this instruction, and we know the offset of the skip label. It is certain that the text section instructions in this file aren't going to get sliced and diced and rearranged among themselves in the final executable. They're just going to be plunked down as one of several coherent code blocks. Thus, the difference in offsets will also be the difference in addresses. The assembler does the equivalent subtraction. It can subtract offsets, knowing that that will be the same result as the subtraction of addresses. So it can complete the instruction with no further help required from the linker, and thus there is no relocation record generated. Now we see another ADR, and again we're trying to get the address associated with a label in the RODATA section. That will again require the linker. So we ask again the linker, perhaps this time in the vernacular for variety, hey, at offset 1C, I can't quite finish this. When you figure out where you're going to put my code's part of the RODATA section, can you add offset E to that address, subtract it from the address you're putting it 1C at, and then fill that into the instruction? Okay, thanks, bye. So this is the same thing that we've seen before of how it deals with the relocation records for data that is in RODATA. The last instruction that the assembler needs help with is, like the previous function call, another BL instruction with its relative address filled in with placeholder zeros, pending that the linker reading the corresponding relocation record and finishing the job with printf's address. This will be exactly the same as we saw with the last two BLs. So in light of that, can you pause the video here to translate this relocation record, as shown on the slide, into a note from the assembler to the linker? As we've seen before, the BL leaves 26 bits for the relative address empty and asks the linker to fill in the relative addresses between wherever it put printf and wherever this instruction is. We finish off with 4 more instructions, all of which the assembler can handle by itself. Don't get scared of all of those zeros in instruction at offset 24. At hex 24. It is not placeholder data. It's just that we're dealing with register 0 and an immediate value 0. For further practice, though, you could, in principle, do exact breakdowns of what we've been doing in these slides and look at every single one of these hex values and make sure you understand what every bit in those hex values corresponds to in this instruction. Alright, so that finishes off the assembler. Now on to the linker, which now, in addition to all the jobs we knew it had to do, it has even more. Namely, it has to deal with relocation record requests from the assembler. The linker takes as its input all of the .o files created by the assembler for all of the files in the program and combines them together. The linker has two phases while considering the merged data from the .o files. First is resolution, which involves resolving references. The second is relocation, which involves moving code around as needed and then fixing the instructions to have actual relative addresses, not just offsets. With these steps, the linker eventually produces the final executable. In the resolution section, where we'll be resolving references, let's think about one specific example of doing so. The linker will notice some BL instructions have a reference to a label that doesn't exist in any of the files provided. For instance, getchar or printf. It will fix this by going out to libc.a, which is just a big archive file made by the AR tool. It's like a tar file, except there's no directory structure. And it will find the corresponding standard library.o file that contains the function's machine code. And then it will add that machine code into its combined text section. If it doesn't find it, that's where you get the not all that friendly linker errors, as shown on the screen here. LD, the GNU linker, returned an exit status to collect2, which is GCC's linker utility. And the error message may be gruff, but I think it's actually really useful. It gives us all the information we want to know. The file name where there's a problem, in this case printf.c. The function name where the code exists that is the problem, main. The offset, hex 10 beyond the start of the text section, and the symbol itself that was undefined, printf. All of these are printed in the error message. So I think that even though it's gruff and it's intimidating at first when you see this and you don't understand what LD or what collect2 are, it actually shows us a lot. And now that you know a little bit more, this is actually a super helpful error message. The second linker phase is relocation, with two jobs. First, it moves code around, because after all, your text section started at offset 0, and libc's text section started at offset 0, but only one of you can actually be at offset 0 from the beginning of our unified final text section. And then, once things are in place, at this point we know the final addresses, the linker has to go through and fill in the missing numbers for the relative addresses that in the text section or the RODATA section to the new addresses in the text section into these instructions that had placeholders in them. Once it's done for all of the object files and for all of the memory sections, it packages up all of this together into the Linux executable file format and completes its work. So just as we could use objdump to look at an object file's contents, we can also use it to look at the final executable. And when we do, we see actual addresses. For example, starting at hex 400710, not offsets from the beginning of the RODATA section, which was starting at 0. Similarly, we can also use it to look at the text section in the final executable, and when we do, we again see actual addresses. In our assembly code, skip was 9 instructions beyond main. At 4 bytes per instruction, that's 36 bytes, or hex 24. We saw that when they were both offsets, main was offset 0 and skip was offset hex 24. Now we have full addresses for main and a full address for skip, but their relative positioning is preserved. The address for skip is still hex 24 higher. 400674 versus 400650. There's also additional code beyond the code that we wrote. Why is that? Well, we already talked about how the linker will have dragged in the machine code for printf and for getchar. It will also have given us some code for _start that calls main in the beginning of the program, and assorted other functions of the C runtime framework. So now, having seen what is there, we should also point out what isn't. Now there are no relocation records left. Alas, this means that Firestone Library will not be able to display the love notes from the assembler sent to the linker. Emily Hale is said. We look at the ADR and we see an absolute address and a note that this is message 1. We look at the BL and we see the actual address and the assembly code and note that this is printf. We're looking good. But let's dive into the machine code one last time, just to see the final results of the instructions that required all of this extra work. First, for an ADR instruction to get the address of a string in the RODATA section. We now know that the current instruction's address, visible here, and we saw a few slides back that message 1, the first real data in the RODATA section, was 400720. We can do the math and get that the former is C8 after the letter. Does the instruction match? We do the concatenation of the green onto the orange, and indeed the relative address is C8. Similarly, for BL, the assembly for the instruction lists an actual location in the new combined text section. We see this gigantic set of leading ones in the relative address. But remember, this is 2's complement, so it's just a negative number. It's the negative of 101, 111, 1. But also remember that to shift left by 2 bits to restore the 2 bits we chopped off because we could due to the alignment guarantee. So this is actually the negative 101, 111, 100. Negative means the location we're jumping to is before the current instruction. This number is hex 17C bytes. So this is indeed what the subtraction 40065C minus 4004E0 would give us. 17C bytes difference. The rest of the instructions are more of the same. We no longer have offsets, we have addresses, and we no longer have placeholder data and relocation records. We have fully fledged, ready-to-run instructions. So this finally closes the book on the 4-stage build process that we've been talking about since some of our first class meetings. And with a thorough understanding of what's going on at the machine code level, you're now ready to go off and write the mini-assembler portion of Assignment 6 in order to generate the machine code for the assembly statements that you want to inject into the grader program for the A and A+ attacks. By completing machine code, this also completes our language level tour, and with it, COS 217 itself. So now we move on to the endgame of the course. Assignment 6 is available. You're able to work on it with partners, as you've been able to for the last few assignments. And we really do encourage you to work with partners. As we've been grading, it's obvious and evident that partnerships tend to produce much better results than working alone. So Assignment 6 is due at 5 p.m. Eastern on Dean's Date. If you do have a late day left, you can take it, but it will only buy you until midnight, 11:59 on Dean's Date. It won't give you the full 24 hours, but on the other hand, it doesn't gain you anything to not use it either. There is no benefit to having leftover late days. Beyond Dean's Date, of course, university policy requires the intervention of your Res College Dean or Director of Studies in order to make further accommodations by the course staff. All right, so I think the nearly 3/4 of you for participating in the survey about our exam schedule, it came out remarkably close to an even split, something like 31, 33, 36 the last time that I saw it. So given that parity, we've chosen to split the difference and go with the middle option of 1 study day after Dean's Date and then a 3-day exam period. That takes us up to the university deadline for take-home exams. We'll have extensive office hours over reading period and especially on that study day after Dean's Date. And we'll announce the exact schedule for that on ED in the coming days. So taking a look back at this course, it's quite broad. It's intent on having you become a more mature programmer in preparation for upper-level systems and application courses that will require you to have honed this tool set is a broad mandate. So I hope that you feel good about yourself for having learned so much material and indeed having persevered through a remarkable Princeton experience that is in unthinkable circumstances. And frankly, a life experience that may well define this generation. I'm certainly in awe of your resilience and the focus shown by students in this course this term in light of all of that looming zeitgeist that's really uncomfortable in the world today. So I congratulate you for coming through this course successfully. I also thank you. This semester has been uniquely challenging, but I've had fun when the opportunity has presented itself to break through the sometimes impersonal wall of Zoom windows and really engage with students in such a way that's reminiscent of office hours and teaching in person. So thank you, particularly those of you who were regular attendees and active participants in watch parties, in office hours for each of the course staff, and in precepts, for making it the most normal that it can be. In this term, I've personally learned a lot about conducting a course as we've adjusted the course topic material in 217 to better fit its purpose within the department, about teaching online and all the differences that entails, and about perseverance. So I hope you can say the same of your own accord, that you learned a lot, that you managed to have some fun despite the conditions. I hope to see you on Zoom during office hours and in the final assignment and for exam prep. So good luck with the end of assignments 5, with assignment 6 and the exam. I really hope that they go well for you. I wish you all the best.